Orbits, Part 2. In this lab, I analyzed orbital motion around a black hole using Python to calculate and visualize how mass, radius, and orbital period relate to each other. Okay. So the main purpose of this lab was to understand how the mass of a black hole can be determined based on the motion of objects orbiting around it. In this lab, I wanted to connect what we've learned in class about circular motion and gravity to something real, like how astronomers find the mass of black holes. The objective was to model the orbits of stars or gas around a black hole to calculate the black hole's mass using those orbits. Okay. The basic idea is that for an object orbiting a black hole, the gravitational pull equals the centripetal force needed to keep it moving in a circle. So by using that relationship, we can rearrange the equation and find the black hole's mass using the orbital radius and velocity. Okay, so I started by reading in the orbital data from the file provided in the lab. Then I calculated each orbit's radius and period and used the standard gravitational equation to estimate the black hole's mass. After that, I made graphs to visualize the results and check that the values made sense. Okay, so the results. This graph just shows the mass of the black hole was calculated for each orbit. The points are mostly flat, which makes sense because the black hole's mass shouldn't really change. It's just oscillating, and the small differences come from things like rounding errors or differences in the orbital data. Discussion. I just focused on how well the theoretical model matched the data. The results line up closely with the expected black hole mass, which shows the math behind the gravitational orbits really works. And the small deviations were due to numerical errors or assumptions in the model. So for possible sources of error, some say the main sources of error include rounding errors in the code, simplifying all orbits as perfect circles, and not including relativistic effects, which are actually pretty important near black holes. We also had a limited data set, so the results weren't perfectly smooth. So the system overview, we had the planet at origin, moon orbiting the planet, and spaceship on the moon. Here you can see the planet masses, as well as the ship mass, and the simulation time was 60 seconds. And our objective was to do a figure-8 orbit around the planet and the moon. So for calculations, you go to F-grav equals gm1 gm2 over r squared. That's the gravitational formula. So we calculated the net forces on the moon and the spaceship, and here you can see my code that I used to do all that. So for initial conditions, for the X it was 5,000, and then for the Y I put it moon speed times 2.0, to keep it relative with the moon. And here you can see the code that I used to get these results. So here are the results. This is what it ended up looking like. Looks a little off, but it's pretty good. Moon trail in cyan and the spaceship trail is in magenta. You can see the 8-figure orbit and the interaction between planet, moon, and spaceship are demonstrated. So for the what if, predicting full system motion requires all gravitational interactions, dominant interactions, planet, moon, planet, ship, and moon, ship. Secondary interactions may affect trajectory, but they would be less significant. So to sum up, the lab demonstrates how physics equations can be actually used to measure something as extreme as a black hole. Using orbital data, we were able to calculate a consistent mass which supports our understanding of gravitational motion.